good morning, good afternoon, good evening, whenever it is you're joining. Thank you for joining. We are covering today a new section and a new packet. We are officially starting the fourth 6 weeks packet. It starts off with section 11.1, word equation. What's for dinner? So our introduction is going to have a quick discussion about dinner and cooking. It's right before lunch, so I think we're all a little hungry. So let's try and get this section out of the way so we don't have to think about how hungry we are. All right, who's going to help me with the introduction about what's for dinner? Hello? Anybody?
Various ways of preparing recipes have developed over the decades. The cookbook shown above was written by a woman who probably collected all her own recipes. Later, printed cookbooks became available. Even guys had no excuse for not being able to cook. Today, we can find recipes in a number of internet sites. We can quickly search for information on how to cook anything we want. Reading a recipe sometimes requires you understanding food codes and symbols, but the information our books start with and what we end up with is there.
All right, thank you. Right? Cooking now is so much easier, right? We can have our iPhone, our iPad, or even our laptop go into YouTube or go into the internet and find a video of a recipe and try it out, right? Cooking has gotten so much more easier now that we have the internet and all the recipes that the internet has to offer, right? So, but anytime you are cooking, you're going to see certain acronyms, certain symbols for amounts, right? That you need to be adding. And if you come in here and if you look at the over here in the last sentence, they're talking about the difference between TSP with a lowercase t and capital TSP. Well, I don't know about you, but I'm thinking, well, maybe they're talking in terms of teaspoon versus the tablespoon. I mean, that's what I think. I'm always getting confused by those two. I'm always hoping that recipes have that B in between the T and the S so that I know that it's a tablespoon and not a teaspoon. Because especially when you're adding certain components of your recipe like salt, you don't want to get those confused, right? You don't want to put a tablespoon that's much larger than a teaspoon of salt because that can ruin dinner just with that one ingredient, right? So we always have to be able to recognize codes. We need to be able to recognize symbols in cookbooks so that we can make sure that we don't mess up and it comes out just the way we want it. All right. So in chemistry, we have symbols and chemical equations that we need to be able to recognize. There's parts of a chemical equation that you need to know the label or the title for. Okay? So this is where we're gonna start our lecture for today. Hey, Miss Caitlin, I'll get you in a second. Just give me let me finish. So chemical reactions. Chemical reactions are happening all around us. They're happening in the device that we're watching this lecture on, right? There's some type of electrochemical reactions that keep our cell phones powered on. There's definitely chemical reactions happening every time you turn on your car, even when you eat your food, right? Or when you feed your dog. Chemical reactions are happening in him or her. But the lecture starts by talking about plants. Okay. And for those of you who came from biology, you definitely studied this chemical reaction that we're going to talk about next. So plants use sunlight to drive their photosynthetic process and produce energy, right? That's how plants grow. That's how they feed themselves. They use that photosynthesis reaction. Cars and other vehicles, they burn gasoline in order to power their engines, right? Every time Salvador gets in his car, in his truck, because I know he drives a truck or a car, he doesn't think about, what's the chemical reaction? Do I have enough gas to drive, to school? He only thinks about that, right? He doesn't think, okay, I need gasoline so that I can complete the combustion reaction that's happening in my engine so that I can drive to school, right? No, he's not thinking about that. He's thinking about, is there enough gas? At least that's what I think about when I wake up in the morning and drive to school. And do I have enough gas to get me to La Jolla, right? Batteries use electrochemical reactions to produce energy and power many of our everyday devices, are definitely our cell phones, right? We need to make sure that it's been plugged in all night, or at least for a good long period, so that it could last most of the day, right? Before I have to worry about that. Many chemical reactions are going on inside of you as well, especially during the digestion of food, right? Every time you put food in your mouth, it goes into your stomach starts the digestion process, right? It starts to break up the molecules, it starts to absorb the nutrients that it needs to keep me fully energized and alive, right? We don't think about the chemical reaction that occurs every time you take a breath. I need to get that oxygen into our cells, right? We don't think about that. It just happens, right? But we know there is a chemical reaction going on. We just don't actually take time and think about it. If you're in math class and you're waiting, you're solving mathematical problems for Mr. Palacios or Mr. Lomeli or Miss Flores, you have written and solved many mathematical equations for them. Well, now, chemists, you got to think about, chemists keep track of chemical reactions by writing equations as well, except our equations are much, much different than the mathematical ones you see in Algebra 1 and geometry and all that stuff. In any chemical reaction, one or more substances, and you got to remember, when you're talking about reactants, you're talking about one or more substance that is present before the reaction has occurred. And I want to emphasize before the reaction has occurred. Okay. Whatever is present before you get started, that is your reactant. Okay. If you run the reaction, right, it goes all the way to completion. Whatever substance one, or substances more than one, whatever has been created after the reaction. Always talk in terms of before the reaction or after the reaction. That's how you are able to distinguish your reactants from your products. Okay? Before the reaction, you got reactants. After a reaction, you got products, right? Really, really easy to remember that. Or at least I hope it is. The general form of an equation for such a process looks like this. So anytime they ask you for a generic version of an equation, you're going to say reactants, arrow, products, or you're actually going to say reactants yield products. Unlike in a math equation, a chemical equation does not use an equal sign, right? You won't see an equal sign when you're working on chemistry equations. Instead, you're going to see an arrow, and that arrow has a name. It's called the yield sign. Okay? Yield sign. And so the equation is described as reactants yield products. All right? If I had sodium reacting with chlorine gas, it's going to yield sodium chloride. Okay? You see how I use that? And I used actual compounds this time. I didn't actually use products and reactants. All right? Any questions on slide number 1? Anybody confused on this one? Pretty straightforward and kind of a review because we kind of already talked about some of these. So here's your first super easy Pear Deck question. Okay, this is where you're starting to participate. And those of you who came late, let me give you the link in case you want to join. All right. Use the vocabulary words below and correctly label the following word equation. Okay, So now your word bank says you got products, you got reactants, and you got the yield. Where do they go? If you have the reaction magnesium plus oxygen is magnesium oxide, which box would you put these three words into? All right. And this one is very simple. I kept it very, very simple because I don't want to confuse you guys, okay? So I got one person writing on Pear Deck. I'm hoping the rest of you guys are thinking about what you're going to write. All right. So you can talk, if you're not in Pear Deck, you can say, okay, in the top box, miss, goes products. In the bottom left, right, goes, yields. I don't know. You guys tell me, where does this stuff go? Where do they go, guys? All right, we got one person done. Who's this? Put your initials here so I can guess who you are. All right, so here we have your reaction, and they've already went ahead and they filled it out for us. Okay. Thank you, Diamante, right? It's got to be you. You're the only one that I have that starts with the letter D. Okay, so Diamante is telling us that magnesium plus oxygen is the reactant, right? Magnesium and oxygen are our reactants. And then she is pointing out that the yield is represented by the arrow, right? Great job. And this magnesium oxide that is produced or is appearing after the reaction, that is our products, right? Or product, right? Because we only got one, but you can have more than one, right? Either way, she has the correct vocabulary words in the correct positions. Very, very good. Great job. Thank you, Miss Diamante. So now we're going into the new stuff, the word equations, right? The new concept. Everything we talked about before, we had already talked about. You can describe a chemical reaction by writing what's known as a word equation. Okay, so, and then they go straight into examples. When silver metal, and this is what we call a word problem, right? When a silver metal is exposed to sulfur, it reacts to form silver sulfide. And you got to remember that silver sulfide is commonly known as tarnish and turns the surface of silver objects dark and streaky black. See the figure below. And I do have a picture of it right here. A couple slides later, I couldn't fit it all. So this is what a tarnished silver, I don't know, object looks like. The picture on the left. And it says here in the description, the coffee percolator. I don't know what a percolator is. On the left has been tarnished from exposure to sulfur. And you don't really expose it to sulfur. It's just sulfur is in the air. It's one of those small amounts of substances that's floating around in our rooms and in the air. So tarnish is the chemical compound silver sulfide. So tarnish is just a layman's terms, right? The same percolator on the right has been polished with a tarnish removal product in order to restore its silver finish. So you got to remember, when it comes to metal compounds, you're going to have lots and lots of atoms of that metal. So if you have a couple of atoms who have created this tarnish, you can basically rub it out, and then just roll it out. Okay, you got to remember those atoms, those elements, they just roll over each other. And if you have the right product, you can remove the tarnish. Okay, all right. And look at that, it looks brand new. Maybe not 100% brand new, but definitely better than it looked like when it had all that black stuff, gunk on it. All right, so the sulfur that contributes to tarnish can come from two places. It says it can come from traces of sulfur in the air or it can come from food such as eggs. Did you know that? Anytime you smell rotten eggs, really what you're smelling is sulfur being released. Yes, eggs have a lot of sulfur. Okay. So anytime they go bad, you'll smell sulfur right away. And it smells horrible. The word equation for this process is as follows. Silver plus sulfur yields silver sulfide. You can also say silver reacts with sulfur to yield silver sulfide. The silver and the sulfur are considered the reactants in the equation, while silver sulfide is our product, and we only have one, right? Another common reaction is the burning of methane gas. Methane is a major component of natural gas. So if you are one of those few people who have still natural gas in your home, which is great because even when the electricity goes out, you can still warm yourself up and cook. It is commonly burned on a gas stove or a Bunsen burner. See figure below. And again, a Bunsen burner you've probably already seen in your chemistry classes in the past or in your science classes. It's basically where we have that fire coming out. Okay, you'll see a little stand and you'll see the fire being burned. A Bunsen burner is commonly used to heat substances in a chemistry lab. Methane is reacting with oxygen to form carbon dioxide, and that's actually what's known as a combustion reaction. Okay, a combustion reaction. The first reaction that remember, all reactions can be categorized into about 5 or 6 reactions. Synthesis, single replacement, double replacement, combustion, decomposition. That was the last one. In this case, you have what's known as a synthesis reaction. You have 2 elements or 2 small compounds creating a larger one. Okay, synthesis means to create. You're creating a new compound out of smaller compounds or smaller elements. Here, the methane gas, like I said, is a combustion reaction. They're very easy to spot, mostly because they have to have the last the 3 compounds. The only thing that's changing is the first one. You'll always have oxygen in the beginning as one of your reactants, and your products are always carbon dioxide and water. That's one of my students' favorite. It's easy to spot. All right, your second Pear Deck question. Use the word bank below to complete this word equation. Hydrogen gas reacts with oxygen gas to yield and produce dihydrogen monoxide. Uh-oh, now you got some compounds, right? You got some names. You need to be able to match these names with with the compounds listed below. H2O, H2 and O2. So, read what you see here and put the correct compound in the correct box. And if you're not in there, you can talk in terms of, okay, box number 1, box number 2, or box number 3. Where does O2 go? Where does H2 go? And where does H2O go? All right. If you're in Pear Deck, and I think Ms. Diamante might already be on the job, she is working on it, and she's probably going to help us out and give us the answer. Thank you, Ms. Diamante. And if anybody else is in there, I welcome you guys to help us out with the answers as well. All right. I'm pretty sure that they're ready to go. All right, let's see. All right, definitely great job. So, hydrogen gas is definitely that H2. Oxygen gas is definitely that O2. And dihydrogen monoxide, I did it on purpose. I put the proper name of water. Very good. Thank you. Thank you, whoever did this. If it was Diamante, thank you. If it was anybody else, thank you. All right. Any questions on that? Any questions? So word equations are great. They're useful. They can tell you, what type of compounds you need, what type of compounds is produced, but they do have some drawbacks. Okay, it's not 100% uh, great. Okay, they cannot be used for quantitative work, and in chemistry, quantitative work, right? Calculations is what we live for. We like to predict exactly how much is being produced, how much is needed, and we always like to make figure out exactly to the decimal point how many grams was yielded. Okay, a word equation does not also tell us how many moles of each material are needed, how many moles of product are formed. Okay. Any questions? Any questions? All right, video time. Let's check out this video. He's kind of funny. Um, let's check it out. Let's check it out. He's really cool. I like him. He's got a lot of energy.
Hey YouTubers, we're gonna switch gears now, switch gears, and we're gonna talk about equations. Boom. So, what is an equation? Well, let's say I'm a chemist, so I research stuff. By the way, let's say a chemist wants to describe this experiment. Well, how is it? I'll be like, yes, first I take this apparatus, maybe this beaker or glass, then I'm gonna have vessel to react it with, maybe, yeah, I'll take this chemical, like I'll need a couple of chemicals, like maybe acid, salt, a metal piece, metal or some sort, but mix it up, and I'm gonna, whoa, man, just explain the experiment? Boring. That's why chemists invented this system of giving information to other chemists about experiments in a nutshell, a very simple way. And that's how chemists came up with equations. An equation is basically an overview of the experiment. A very quick overview. And with that experience, you can already guess what you need to mix, what you need to do during the mixing, what you need to make out of it, how you purify stuff, all that. Because what is we're concerned about is how you change and make new stuff. Alright. So equation is an overview. So in any overview, when you do an experiment, you need raw materials. Alright? You need something to start. For example, let's say I have a piece of chicken, I got some oil, I got some sauce on the side and stuff like that. And I want to make grilled chicken. Alright? So all that chicken, sauce, all that seasoning stuff, these are the raw materials. And in any equation, you have an overview of the raw materials you have. And these raw materials are called reactants. Things you start off with reactants. Alright? And then after I cook my chicken, boom, a delicious piece of grilled chicken with the eggs on top of it, seasoning, and wow.
He's making me hungry.
I can almost smell it. So what I get out of it are my finished stuff, my finished product. So this is what you need. You get your raw materials, and then when you do the experiment, you get your products. So the equation will represent this in one line. You get your starting materials, your reactants, and then the products. Now, to get from your reactants to your products, you need a signal to tell other chemists that you're making something. And we represent the making of something by an arrow. This arrow means yield. Yield. Okay? And so when you get your raw materials, your reactants, and then you yield products. This short one is an equation, an overview of the experiment. What type of equation talk about now is bunch of words with an arrow and a bunch of words. So, for example, I have, let's say, hydrochloric acid, okay, plus alkaline, let's say sodium hydroxide, or some of these things are secondary. And I get, let's say, sodium chloride. Now, I'm writing this really big, so it doesn't fit in one line, but it should be one thing. And, right? Here is the word equation. So I took that acid, mix them up, boom, salt, alright? Notice what's about this word equation do you see? What do you notice about it? Well, first of all, you gotta map all means for them. All these reactants, products. So anyway, the word equation is not taking much about the experiment. For example, how much of this one? How much of that one? How much of this one be? Could be good, alright? Okay? And also, it doesn't tell us anything about procedure, like the hits. Heat, catalyst. I don't know. What about other information? What's the physical state that hydrochloric acid is in? What's water happening? Is it ice water? Is it liquid water? Is it gaseous water? Or vapor? Nothing is said about the wave equation. So a wave equation, it has its good points. It's just a very, very extremely basic overview of a typical experiment. But it has quite a number of downsides. However, you still need to learn this in order to pass your exams.
I missed it. Darn it. I guess I'm gonna have to click on it later. Oh, there you go. Okay. I just want to make sure I can save it for later. All right, so let's close out today's lecture. Summary: word equations are used to describe the conversion of reactants to products. Your review questions. These are the 3 questions we're going to tackle today, and they're very, very easy. Write the generic form of a chemical reaction. Number 2, what are reactants? Number 3, what are products? All right, give me a